This is Set Operations 1. We're going to learn how to use sets and Venn diagrams to model sets to find out if things are equal, to find out if sets are equal, and to explore a little bit what it means to have intersections and unions and ands and ors. So let's start. The intersection and union of sets. The intersection is a common region. The intersection of two sets is where they overlap. So the common region is what they share. So what sets share is the common region. The union, however, is the compilation of sets. I'm going to call it everything together. Because when you do the union of sets, you put everything together in the same pot and you say all of them. The intersection would just be what's shared by those two sets, the same things from each set. The intersection of sets is like where streets cross. It's where streets cross. It's everything that is shared by those two sets. A picture of that would look sort of like this. And I'm going to be using Venn diagrams to kind of model these things. And so I've got two sets, A and B, both in the universal set. And the intersection of those two sets is going to be just the stuff that is shared by both sets. Sometimes there's nothing that's shared. So disjoint sets have no shared elements. So they have no shared elements. So for example, when I was up here talking about where streets cross, what I might say is the intersection of sets is A and B. So this N symbol means intersection, or A and B equals shared numbers or elements. And so if I have two sets that don't share anything, if they have no shared elements, this would be the empty set. So the intersection of disjoint sets is the empty set. Because if they don't share anything, then where they cross would be empty, so it would be the empty set. This brings us to the discussion of the union of sets. It's denoted A union B. It is a set that contains all A and all B. So that would be all A and all B. The picture of this would look like the one above in a couple of ways. Still talking about two sets, A and B, except the union is going to look like this. It's everything in A, everything in B, all put together. That's what it looks like. It's all of it, all together. Not just the intersected part, but everything else. When we put some numbers with this, let's see what this looks like. We're going to remember, of course, that when we have the n, it's like steak and shake, it's intersection. And the u is union. And so if I say A and B, that's going to be the intersection of A and B. It's going to be a set. So if I look at A and B, I see that 4 is shared, as is 5. So the intersection of A and B is going to be 4, 5. What about A and C? Let me erase these circles. Let's look at the intersection of A and C. 3, 6, 9, 1, 4, 5, 7. So the intersection is going to be the empty set. These would be disjoint sets. They don't share anything. So if they don't share anything, then the intersection is empty. So they're going to be disjoint. What about B and C? I see a 6 here right off the bat and a 6. I see the 3 and the 3, and that's it. So the intersection here is going to be 3, 6. What about A union B? That's everything in A and everything in B. Once again, let me erase these circles. And we're going to put down everything that's in A or B. So A is 1, B has a 2, and a 3. They both have a 4, a 5, a 6, and a 7. 1, 2, 3, 4, 5, 6, 7 is going to be both of them together. That's all of the elements in A or B together. What about A union C? Now notice when we had intersection they were disjoint, but because it's union we're going to put all of them together. So A is going to be 1, and B's got a 3, there's a 4 in A, there's a 5, a 6, a 7, and a 9. That's everything in A or C all together, one big set. What about B union C? B union C is going to be 2, 3, 4, 5, 6, and 9. Everything all together. Intersection is what's shared. Union is everything together. Go ahead and try this one down here that I've put a star by on your own if you feel like you need another example. We're going to keep moving. And or. This is really kind of an interesting concept because sometimes we don't want to write intersection or union, and so they come up with these words that mean what we're talking about. And is going to be used for intersection. So intersection is and. What is in A and B? And or is going to be union. What is in A or B? Put all together. This is pretty self-explanatory, and this is going to look like this, A and B, and this is going to be A or B. That's what this looks like. And so if I'm going to write sentences that describe these sets, I'm going to use that same principle to look at these symbols here. Well, union is or. So this is elements in A or B and C. See what I did? A, elements in A or B and C. What about this one? Elements in J and not in K. Because remember, when I'm talking about the complement of a set, it's not going to be in K. So if I'm talking about the complement of K, it would be what is not in K. So this is elements that are in J and not in K. What about this next one? Elements in D and are not in E or F. When I write it this way, what does it look like? Well, it looks like I'm saying they're in D, but they're not in E, and they're not in F. So I need to write this in a little bit more clear way, because really I'm only talking about the elements that are not in E, but they do need to be in F. So let me write this a different way. We have to be careful when we're writing these things, because they might not be clear. And so elements in D is good, and are in F, and not in E. You see how that's much clearer? Because I do want the ones that are in F, but I want the ones that are not in E. So that's an exercise in writing clear definitions. What about this? Elements not in L or M. Is that clear? Ask yourself, is there any confusion that could arise? Well, what I'm going to say is, if it's not in L or M, that means not in L or not in M. Or does it mean the other way around? So we have to be clear. What if I said this? Elements in M, but not in L. How about that? Or elements in M, or not in L. See how that works? All right. The way that we evaluate those kinds of statements is using Venn diagrams. And so if we are looking at A union B, or A or B, is it equal to A and B? Is it always true? Well, what about this? What if A equals 1, 2, and B equals 1, 2? Then yes, the intersection, 1 and 2, is also equal to the union, 1 and 2. But what if A was equal to 1, 2, 3, and B was equal to just 1 and 2? The intersection would be 1 and 2, but the union would be 1, 2, and 3. So this would be no in this case. And so sometimes we really need to use Venn diagrams to figure out if these are actually equal. Let's look at what this means. Or look at what this does for us. I'm going to draw 2 Venn diagrams here. The first one is going to look like this. Here's A, here's B. I'll use red. A union B. And this should actually have a little prime next to it. A union B, not in A union B. So the part in the circles is A union B. So the part that I'm actually looking at is this part here. Right? Everything outside the circles. Because everything outside the circles is not in A union B. So that's all the stuff outside the circles. Well, what does this other one look like? I'm going to draw A and B. And if I say not in A, everything not in A is this part here in red, right? Because all this stuff is not in A. So everything in B is not in A. Everything out here is not in A. It's just everything that is not in A. And the intersection of that and what is not in B, well, everything not in B would be this stuff here in the blue, right? And so because this is the intersection, I want everything that has red and blue. Well, if I look at everything that has red and blue, this is just this red part out here. Everything that has red and blue in it is just the part outside the circles, because this has just blue and this has just red. And so yes, these sets are equivalent because the intersection of those two sets is the purple part here that's got the red and the blue. Well, that's only the stuff outside the circles. So that's good. That means by showing the Venn diagram, we were able to see this. Let's look at this next one. We'll draw a couple of Venn diagrams. And in both of these cases, we're still only using 2 different sets. Eventually we will get to using 3. A intersect B prime. Well, A intersect B would be this part here. So it's everything but that part. So I'll carefully color around that part. So A intersect B, I want everything that's not in A intersect B. Well, that's just all this stuff, right? Everything but that middle part. What about A not in A intersect not in B? Well, I'll do this. What is the stuff that's not in A? Well, not in A is going to be all this. Not in A. So that's everything that's not in A. And let's look at everything that's not in B. Everything that's not in B is this part here, right? Because B is this circle-y dealy here, right? And so it becomes clear what is the only part that is not shaded at all. The part that's not shaded at all is just that little middle part, right? And so yes, these are equivalent. These sets are equivalent because the only part that's not shaded in both of them is this little middle part here, right? It's going to take a little bit to get this. But if you remember that prime means the complement, which means not in that set, and you're overlaying that shading with the stuff that intersects or the stuff that is unionized, then you can start to get this, okay? So watch this again if you need to, and make sure you do that sample problem, and we'll see you next time.